Hey everyone, I'm Zhongtang. I'm from Purdue University, and today we'll be talking about oracles and TLS oracles in general. Does this work? Okay, it works. So oracle. I'm sure half of the stadium already know what the oracle is, but just to recap. An oracle helps us to pull information from the traditional website onto the blockchain. The two major examples are exchange rates. Let's say you want to have some exchange that helps people to convert their currencies, maybe from Bitcoin to Ethereum or the other side. Then you will need, obviously, you will need information on what the ongoing market exchange rate is, especially given the recent, the recent downfall of a lot of cryptocurrencies that's happening yesterday. The other example is a prediction market. Let's say we have predictions about this upcoming US president election and want to know who actually win the election. Well, that's obvious information, right? That's very apparent on the traditional website and everyone probably knows about it. We still need some way to put that information onto the blockchain. And that's what Oracle is there for. Needless to say, there's already easily tens of companies and stuff that's been working on Oracle in general, like Chainlink, Super Oracle, Polyhedra, Reclaim, and also a lot of prediction market, like Polymarket, Manifold. I'm sure while I list a lot of things here, I'm sure I'm still easily missing like tens of the companies and startups. So yeah. With that being said, let's say we want to pull more information from the website. So imagine that with all the e-commerce, e-banking, e-government that we have right now, it's very easy to, let's say, curate your credit score online. It may be easy to verify your age with government online, or immigration status, or anything that you can think of. However, it's not very obvious how we can put those information onto the blockchain. Well, obviously, you can just provide your bank credential, and then people will be able to verify your bank information. But I'm sure that's not what everyone wants, right? Nobody wants other people to be able to use your bank account or even see some of the more sensitive information. So how can we pull more information in this way? That's what the TLS Oracle is for. So we can imagine that some user, such as me, were to talk with the bank about my credit score. Maybe we can have some sort of oracle that chips in to this communication. The oracle can maybe see our communication with the bank, and then at the end of the communication, be able to say something to the blockchain, like maybe about my credit score. Maybe the oracle will be able to say that my credit score is good enough, such that I'm eligible for some offer on the blockchain. Well, there's a few caveats in this scenario than what you might be thinking. Well, the first thing you may be thinking is that, what if we just use the TLS transcription? Can I just post my TLS transcription to the oracle, and then somehow he will be able to verify that the bank told me what he has told me? It turns out that this is not so easy, because TLS is a symmetric encryption. This is cryptography session, so there will be cryptographic jargons, if you will forgive me. I'll try to explain them. The caveat of TLS being symmetric encryption is that if I'm some bad guy, I'm an adversarial user, I can produce any transcript I want, giving my handshake with the server. So if I just somehow communicated with bank and bank told me I have very poor credit score, I can actually flip it around and produce a transcript that I have very good credit score. Well, that's obviously not very nice, right? Because nobody wants to have a system that's not sound at all. So based on that, we know that the oracle has to be involved in the communication in some way if we don't want to ever change the TLS protocol. So the other caveat here is that you'll be thinking that what if the bank could sign on my credit score? Then it provides a non-forgeable kind of proof that my credit score is indeed my credit score. However, if you think of your e-bank experience with the bank, You're going to post to the bank in maybe some HTTPS request, and the bank is going to give you maybe a JSON response. The bank is not going to be kind enough to actually sign on the JSON response, right? Because if you think of the traditional query scenario, the bank has no business in proving that your credit score is your credit score. This information is for your eyes only. It's not supposed to be published on the blockchain space. So here, we want to be able to do that without involving some sort of expensive communication with the bank, like trying to bag the bank into providing information for the blockchain. So we can easily imagine some sort of oracle that sits in between the user and the server here and acts as a proxy, like HTTPS proxy between the two sides. This way, hopefully we have all used enough VPN and proxy and whatsoever that we know our information is still relatively secure because TLS is an end-to-end encryption. In that even if someone sits in the middle and forwards the proxy tags, he has no information about your secret bank credential or something you don't want him to see. But at the end, we want to also have this functionality where the user can just review the needed part of the plaintext, maybe his credit score, at the end to the oracle. Obviously, it comes with some proof, right? Maybe we're able to be able to decrypt it in a zero-knowledge way such that the oracle is convinced that I do have this much amount of credit score that I want to prove. So now, with this out of the way, we have one very big question that's been asked thousands of times in the cryptography field. Is this design secure? So very funnily, it has been conjectured very, very long, since DECO in 2000, that this thing is actually not secure. Why? Because around that time, there's a very famous attack on Facebook called the key commitment attack. That is, for the same ciphertext, we might be able to have two different keys that are able to decode them into different plaintext. If you think of it, it's kind of in a niche interval between what we traditionally consider the AEAD secure and what we traditionally consider insecure. You know TLS is end-to-end encryption. It also guarantees integrity. That means we cannot arbitrarily just act as a middleman, change the response, and the client still accepts it. However, here, the attacker is the client himself. He knows the key. With that additional information, the client might be able to produce a different plaintext with a different key that somehow still corresponds to the same ciphertext. So here, that extra information about the key, about the original key, actually is the difference. So this is a very famous attack. When it came out, a lot of people were pretty surprised. And I will not go into the very interesting story of how that attack came into being. But since that attack happened, people have conjectured that whatever this model happens, the user can just be able to decrypt the same ciphertext into different plaintext with different keys and somehow be able to fool the oracle. Because the oracle here does not have the TLS symmetric key. So he cannot even possibly know what the plaintext the user originally received from the server. So ever since that, there has been a whole lot of work just to ensure key commitment, just to ensure that such attack does not exist in our proxy-based TLS oracle. We have DECO, which is obviously the opening work of the field. We also have people trying to do a lot of MPC stuff, like gobble circuit, and so on and so forth. We also have a lot of zero-knowledge proof in the other direction. They just try to prove that, the key I zero-knowledge to the oracle is indeed the key that we're trying to communicate between each other, all in a very zero-knowledge fashion. So there are so many zero-knowledge involved, and I'm sure you understand this is kind of a cryptographic intensive process that a lot of people has been doing. But is it really insecure? Now I see, I trust from the title, you're kind of seeing where this is going. But to answer this question for once and for all, we kind of need to enter the cryptography territory. Now we're kind of trying to do math here. I will try to keep it short, but it is what it is. So let's start with one popular fix on key commitment. It's called padding. That is very simple. We just need to add some amount of zeros to the front of the plain text. And when we decrypt it, we make sure that this amount of zero is still present in the decrypted plain text, obviously. So the rationale here is, even if we are somehow able to come up with different keys that decrypts the ciphertext, it's hard to decrypt the same ciphertext, the same plain text with different keys. Right? Because what we are saying about key commitment attack is that we're able to decrypt the same ciphertext into different plain text with different keys. So the rationale here is that if the plain text is fixed, it's the same, it's all zeros, then it's kind of hard to decrypt it into the same, this thing with just different keys. And now we can I'm trying to show the intuition of why this is hard. Let's take an example of AES GCM, which is the most popular cipher suite used in TLS. So in GCM, the ciphertext block is encrypted by this formula, which is basically saying that we have this cipher, we do this on some nonce, and then we XOR it with the plain text to get the ciphertext. Now, since let's say we're trying to encrypt the same ciphertext to the same plain text, we can kind of cancel those out and get the equation down here, which is basically just to say that we are able to come up with a key nonce pair that somehow has the same result after this AES cipher. This is not actually for one block. It's actually for the padding amount of block, B blocks here, because we're going to decrypt them to all zeros with different key and nonces. Now, if we model AES as kind of an ideal cipher, since no one knows how to break AES, apparently. So the definition of an ideal cipher is that there's no way to know the permutation without testing the key themselves. That it's not possible to say that, hey, I want this cipher, please give me a key. Right? Then if we think of this cipher as permutations, right? Because for a cipher to work, it has to be able to go forth and come back. Then we kind of need, based on this equation, we can kind of see that we need consecutive blocks to happen to permute to the same thing. And this turns out to be kind of hard, right? If you think of AES as like 128 bit blocks, and you need kind of B blocks to be the same, like let's say 8 blocks to be the same. And you cannot actually do any meaningful computation because AES is kind of random. There's no way to know what's in the permutation without actually testing the key. And it's essentially just down to some luck. It turns out that this amount of luck is enough to keep the cipher suite being key commitment. Now let's go back and take a look at HTTPS. Here I use Postman. I made 2 requests to Google and Twitter. I mean, it should be X now, but the Twitter also works. And here is the prefix of the HTTPS response they sent back. Now, if you look at this very hard, you don't even need to look at this very hard. You can already see a pattern. You can see that it's kind of padded with all the HTTPS 200 data and so on and so forth. We can go back and look at documentation, but obviously for HTTPS response to work, it has to start with the status code, or otherwise it doesn't work. And most do start with data. Funnily, this is actually a recommendation from IFC that any server with good practice should start with data. I have no understanding of the underlying mechanism, but that is the recommendation. And that seems to be what most servers follow. So if we give a very generous consideration of all the status code, the 63 of them in total, And if we keep the date for the last hour, let's say we reject any response that's not in the last hour, it seems that for the first fixed amount of bytes, there's only a very limited amount of possibility that can happen. Our paper kind of formalized this. We define this as being variably padded, which means it's kind of padded. There's some wiggle room around, but not too much. Or not too much to affect the security in general. And based on that, since we know that padding is already enough to ensure key commitment, we're able to prove that for HTTPS, which has variable padding, as long as the server is correctly working and not just responding with garbage, the proxy-based TLS oracle is also secure. Now, if we think of being banks and government and all the stuff, and what we do use from day to day, I trust that you have found this HTTPS scenario covers almost all websites. Now let's take a look at the non-HTTPS scenario, which is more niche, but remains an interesting case. In this case, we do see those key commitment attacks happening. Here's a concrete example. Let's say I'm an adversarial user. I can handshake with the server, get a key, and use that key to derive a pair of very specific plain text. Here I have dad and beef, just for CTF jokes. And then I can kind of, if I back the server to send me dad, and the server do send me dad, I will be able to prove beef. It is a very specific attack scenario, but we also want to understand how likely will this attack happen. To do that, we can kind of separate the data we have into two categories. One category we call it malleable, because we can easily change the value after we establish the handshake. Let's say it's account balance, then we can kind of handshake first and then do some withdrawal or deposit. If it's a bank statement, then maybe we can handshake first and then somehow be able to tamper with it. And we know that it's insecure because the attack we just described can easily happen. I can easily do a handshake, try to alter my balance, and somehow be able to prove that I have more money than I could feasibly have. But on the other hand, we also have things that's relatively fixed. Let's say account number or age. If I can create new accounts every second, then I'm not going to have that many account numbers, right? If you consider the case of age, I'm surely not going to age 1 year per day, so my age is also not going to change very much. What we want to know is that if our attack is still feasible in that scenario, when the data is fixed and not changeable after the handshake. Well, it turns out that for these kind of fixed data, we only need a weaker version of the key commitment property. We can kind of refine this as being context unforgeable. Or for informally, that for some kind of fixed plain text, it's hard to find another plain text that matches the same ciphertext. You can see where the fixed data come from, right? We already fixed some plain text beforehand. I would liken it to the second pre-image resistance in hash functions, in that we have some sort of value, and we're trying to find another value that hashes to the same thing. It turns out that there's an interesting differentiation between AES GCM and CHA-20 poly, the other also very commonly used cipher 3 for TLS. Namely because AES itself is a block cipher, which as we already see is a permutation that is reversible. But CHA-20 is based on a pseudo-random function, which means it's not reversible. If we somehow smash it into a new thing, it's not able to come back. It turns out that this differentiation is meaningful enough to cause the two cipher suite to be one not secure and one secure under our definition of context unforgeability. Therefore, for AES GCM, it cannot be used in HTTPS scenarios, even with fixed data, because we're still able to somehow come back given some fixed data and try to derive a new key that gives a new plain text. But for Cha-Cha-20, because we cannot actually come back from the fixed data, it turns out it can be used in non-HTTP scenarios, given that our data is fixed. So the takeaway here is that we're trying to implement some sort of proxy-based TLS oracles. And we have categorically proven that for HTTPS, as long as the server is a correct server that does not do weird thing, it's secure. And that should cover almost all use cases we could ever feasibly think of in an oracle scenario. For the non-HTTPS scenario, we need to give it a little more thought. It's kind of secure as long as we can make sure the data is fixed and we can use the correct cipher suite. Otherwise, we have the very specific attack that could bypass the security of the oracles. I had the luck to work with a very talented team. Specifically, my advisor here, Professor Kate, will also be talking about wallets and multi-device wallets tomorrow. I highly encourage you to go to that talk. I think it's in the first session tomorrow. And I will put out the preprint and the slides here, just in case you want it. That's pretty much it. I think I still have some time to take questions, maybe 5 more minutes. And yeah, let's just see if anyone wants to ask anything.
Thank you, Zhongtang, for the short and nice talk. We have time for questions.
Very nice talk. So when you need, of course, multiple of these sort of attesting nodes in the middle. You'll do them in sequence, I presume?
It can happen either in parallel or in sequence, but yes, you need multiple nodes. Actually, the one assumption of this oracle thing is obviously that a majority of the oracle is correct.
Okay. Yeah, I mean, in sequence, if you do them in parallel, the user has to have multiple interactions, yes? Well, anyway, if you're going to do them, assuming there's no loss doing them in sequence, and you can do them in sequence, an amusing like deployment strategy might be to fork a Tor client and integrate it that way. So anyway.
Yeah, that could make sense, but for Tor, you're also trying to add encryption every layer because it's the kind of like an onion, right? Yeah, and you can kind of do a proxy thing with Tor for sure.
I have one similar question. Can you explain a bit more about the threat model? Whether you are trusting the oracle, is there a single oracle? There will be multiple oracles,
so we're not for this paper. The slide disappeared. Okay, that's fine. So obviously, in this paper, we're focusing more on the cryptography aspect rather than the threat aspect. But so basically, we're trying to say that what happens is that if the oracle is correct, the user cannot prove wrong things. We do not make any guarantee when the oracle is not correct, because then they can just collude together and do whatever they want. But if we're going to deploy it in real life, like any oracle, we're going to assume that there's a majority correct oracle, that the user makes a test to all of them, and like by a vote of majority, you can able to prove things.
Okay. Any more questions? If not, let's thank Zhongtang. Oh, we have one question here from Don.
Thanks, Saurabh. So this is a wonderful talk, wonderful result. It's very optimistic if you want to build things out of TLS. It's also absolutely terrifying in a different respect, because it means if you try to do something like build a voting system over TLS, now you are bound to the vote that you sent. You're able to prove it to other people. So there is a body of research looking into deniable encryption to get around situations like that. So I'm just wondering, like, how do you place this and interpret this in that setting? Is your result basically saying we are now unable to deny votes and that sort of thing? And to take it a higher level too, which is a little more technical, is there any wiggle room in, say, negotiation of algorithms that you use as opposed to changing keys? Maybe changing which algorithm you do, and you use a key commitment with one algorithm, or avoid key commitment by pretending you used algorithm A and using that key or a different key with algorithm B. So I'm asking, is there wiggle room to get back to deniable encryption here?
I think for deniable encryption, you do not necessarily need to use HTTPS necessarily. I don't know any popular voting that's conducted with HTTPS. I know certainly the US election does not allow you to vote online. So if we're able to think of it in a DAO sense or in a more futuristic sense, we can certainly design deniable encryption without engaging in HTTPS or any of these things. I mean, we can always come up with our own cipher that can satisfy whatever requirement there is. I think the thing has a premise is that we have to build this based on existing infrastructure. But since such thing does not exist, I don't see why we need to do that in the first place. Because for e-bank and e-government, they exist. So we're trying to find ways to use them without having to nudge them toward the blockchain direction. But if it's voting and something that does not exist, I don't see why we can't just come up with new schemes that allow us to achieve a greater level of privacy and security that we want.
Thank you very much.
Okay, let's thank the speaker again.